Virtually just go.
All right. Hello, everyone. We will get started with this workshop on microphones and NES controllers. So this workshop's going to be fairly straightforward. Basically, I'm just going to I'll switch between the slides where I have some basic information about things we're doing and Quartus, where I will actually show you guys how to do things. So we will get started. Yeah, microphones and NES controllers. So first of all, brief announcement. Some of y'all have signed up for design reviews, and by some of y'all actually looking at here, there's no one who has signed up for a design review. But anyway, design reviews. Please make those design proposals and sign up soon. We would like to have all of them done through the end of week 10. We will do them in spring break if we really have to, but we'd rather not spend our spring break doing design reviews. And starting next quarter, unless you have a really, really good reason for needing your design review that late, we will probably not do it and just make you do the regular DAV track. So please get those proposals in soon. Sign up for a design review this week or next week. We have a spreadsheet that we posted in an announcement with all of our availability, and I'll post all that stuff again after this workshop. So yeah, that's it. And then now, microphones. So first of all, microphones, you guys probably know what microphones are. They will pick up sound and output electric signals. There are two different kinds of microphones that we've used in all of DAV. There's the digital microphone and the analog microphone, both of which are pictured here. So, yes. So this is a digital microphone. Basically how it works is it picks up sound like a regular microphone, and it has an ADC, an analog to digital converter, built in on the little board. And it will convert the microphone input and then output just bits using the I2S protocol. This is a microphone that we used 2 years ago and the year before that, and basically every year until last year for DAV. And so in order to interface with this microphone, we would need to output, or we would need to write a driver for I2S the way we did in lab 4 for I2C. So there's quite a few advantages to digital mics, mainly that they're far less complex because you don't need to worry about digitizing the signal yourself, because obviously the board does it for you. In addition, they're more resistant to noise because in general, digital signals are more resistant to noise than analog ones. Analog ones tend to become noisier as they propagate over a long wire. And lastly, you can usually just find serial communication code online, which is really nice. And then you can just use that for the digital mic and it saves you a lot of time. And in fact, in the history of DAV, only one person has ever actually managed to make a working I2S driver, and every single other person in DAV has stolen the I2S driver from that person being the person who created DAV at the very beginning. So the question now is, could the second one be you? And the answer is no, because we will be using analog mics instead. We will not be dealing with that. So this, on the other hand, is the analog mic. This is one you should find in your kit. Oh, Parth, question.
But what if we want to use the digital mic and just take the code from the person who created that?
There's literally no reason to, but if you want to, and you want to take the code, we will let you do so on the condition that you do not ask us for the code, because Claire and I don't have it. You will have to find it yourself. Sanjit. On the FPGA, I think it's 12 bits, and the ADC runs at 1 megahertz or something like that, and I don't know what it is on the digital. Jerry?
Wait, on FPGA, is it like a separate chip or is it IP that's
It's an IP. We'll get to that later. But yeah. So this, on the other hand, is an analog microphone. It takes sound and it outputs an analog voltage on the out pin. So now we can get continuous audio signals, but since we live in a digital world in DAV, we must digitize and sample the signal ourselves. So our digital microphones had an ADC on them, our analog ones do not, but we will use an ADC on our FPGA to sample the microphone. So now the reason we use analog mics over digital mics is because, well, one, the output of an analog microphone is a little bit more faithful to the original input signal, because of course it's an analog signal. That doesn't really matter as much because we're going to be digitizing it anyway. But the other nice thing is analog microphones have fewer silly little pins to deal with. And in reality, hooking up an analog microphone to your FPGA is really easy. So lastly, analog microphones don't require that we learn how to use I2S or even that we find code online or from someone else for I2S, because other than this particular use case, we've never used it in DAV. It's a very unused and esoteric protocol. Here's a brief summary of digital versus analog mics. Claire added that herself. I didn't even know that that was there. Yeah. So like I said earlier, digital signals resistant to noise. We don't need to digitize the signal ourselves, but making a driver for those microphones is particularly difficult. On the other hand, analog mics have more faithful representations of the original signal, and you can control things like the sampling rate, and the pinout is also less complex. However, the downside is the analog signals degrade over long wires, but our wires are short, so we don't care. So if you go into Quartus, as I will demonstrate and very soon, you can find an ADC controller IP that we will use to digitize our signal. This is the configuration for the ADC. Again, I will open Quartus like RN and show you guys that this is a thing we can do. And then if you have your FPGA with you, you can also connect your microphone to said FPGA, and we will try to make it work. But yeah, okay, so we will do that now. I will change screen sharing to Fortus. Right. New project wizard. And I will just speedrun creating a new project. Project. This is max 10. If you guys have wait, oh, you guys can't see my screen. Hold on. That's really funny. You can see my screen now. All right. Yeah, so now I'm creating a project. We will search for this one, and then simulation Questa, but also we're not going to be using simulation for the mics because it takes about 5 seconds to set them up. But yeah, anyway, now after we wait for the 30-minute waiting period for Quartus to create a project, we will set up the ADC together. Lovely. Now, new file, system verilog. All right, so here's what's going to happen. Module, mic, top, and we'll worry about the inputs and outputs later. But the main thing is right now we're going to go into the IP catalog and create an ADC. So this is going to be, I think it's in, might be in tools. Yeah, it's in tools. Tools IP catalog. If any of you have created a PLL so far for one of the other labs, you will know how to do this already. If not, well, this will demonstrate how to create an ADC in the IP catalog. And then when we're doing the NES stuff, I'll demonstrate how to create a PLL. But yeah, go here for the IP catalog, and then it should open up something where you can search for ADC. And you should find something like, yeah, ADC controller for DE series boards is the one that we're looking for. And if you just double click that, it'll open this. Yeah, okay. So now we have the ADC configuration tool. If you'll notice, our DE series, oh, well, I have to fix this first. So Entity name, you can just call it like ADC or something. It doesn't really matter. Target device. For some reason, this is like not expanded on my computer, but I will just expand it. There we go. And then now if you go here, make sure you specify DE-10 Lite and 10 megahertz for the ADC clock frequency. Number of channels used, we will use one channel just for our microphone. And then the system clock frequency is 50. And that is literally it for configuring an ADC. You might be thinking, why didn't we just make this slides instead of a demonstration? The reason is because last year it was slides and just not a demonstration. And we didn't know what we were doing. Neither did anyone else. So generate now. In simulation model, you can ignore that because realistically, you probably won't need to simulate. One of these days, this will finish. It is finished. All right, so now if you look in IP components, hello. Oh, right, because you have to add it manually. So now if we go to add remove files in project, we will be able to add the IP that was just generated. Because for some reason, the ADC does not add itself, unlike everything else. So I think we will just go here, add this, apply. And now you can see ADC controller for DE series boards shows up under our IP components list. So now that we've done that, we're going to write the actual top level for our microphone, which is fairly simple as well. You're going to want to give it an input clock. That's going to be your 50 megahertz clock. You're going to want to give it an input ADC clock, which is also separate from your 250 megahertz clocks. We have a 10 megahertz clock that's exclusively used for the ADCs. And then we'll output the microphone on the LEDs. So now if you want to see how to instantiate this ADC, it's not here. I did not mean to open that. That will probably cost us about 27 months. All right, so now what we will do is I will go and open the actual Verilog file for the ADC, which should be, I think, this. Yeah. So, wait a minute. Why does it have 8 channels? Here, let me go and verify that I made it says 1 channel. Because I think it should only show 1 channel there. It's also possible that I'm lying to you. Okay, it says 1 channel. I'm lying. I'm not lying to you. Anyway, so now what we're going to do, this is our ADC module. So you will just instantiate it as any other module, right? You take module name, you give it some instantiation name, and then it takes a clock input, a reset input, and all the channels as outputs. So what we're going to do is we are going to create a wire, give it 12 bits, and then the ports for this are just going to be ADC clock for the clock. We can actually give it a reset button, but I'm just going to give it 0 for no resets. And then for the output channel, we're just going to go mic output. And then now we will just assign the LEDs our microphone output. And if you can plan this correctly on your FPGA, it will just work. We will give you a chance to do that after the workshop. And yes, the microphone output is in fact 12 bits. So when we're putting it on the LEDs, typically we just put the top 10 bits or the top 10 bits. Save that. Yeah, this is the entirety of setting up a microphone for a digital audio visualizer. It's very convenient. And this is also why we use the analog mics and not the digital ones. The digital ones were more annoying than this. But yeah. Okay, and with that being said, we will come back to this after the workshop for anyone who is making a digital audio visualizer to set up a microphone, or if you're just interested in setting up a microphone on your FPGA, we will do that after. But for now, we will move on to the rest of the teaching on how NES controllers and other controllers in general will work. Right. Before I do that, let me unscreen share Quartus. You guys can see that. And yeah, okay, the people on the Zoom can as well. All right, so next we will move on to talking about the NES controllers. So before we had like I2C and other fun protocols, video game companies and like anyone else making a peripheral, they kind of just did whatever they wanted, which is unfortunate because we like rules in DAV. We're an orderly society, and therefore we must figure out these rules even when they don't exist. So even the NES controller, which like I just said, doesn't really follow a standardized protocol, it still has like actual rules for how it works, right? Because ultimately, if you want to be able to communicate between two devices, they both need to know what how the messages will work. So if you were to take apart your NES controller with a screwdriver and just like look at the PCB inside, you would probably see one of these. This is a shift register IC, specifically the 4021B. The reason we know this is because Claire and I Googled it and found a website that told us. But before, obviously, the person who made this website that told us how this worked had to do something to figure it out. So this is probably what they did. For really simple controllers with just a few really basic ICs in them, you can usually just unscrew it and inspect the internals to determine how it works, right? Like in the case of the NES controller, you look at the inside, there's one IC on a board with some resistors. You look at the IC, you like Google the model number, and it'll take you to the data sheet for a 4021B shift register, which is usually an indication that the IC is a shift register. So first you figure out what's inside, then you can find the data sheet for these internal components, and you can figure out the clock speed and pin out from that. So we will quickly look at the data sheet because this is an essential skill to have.
Wait, can you repeat again? Why? What was the line you said? Like, we could guess it's a shift register because.
Oh, I was making a joke. I said we can guess it's a shift register because if you Google the model number, it'll tell you it's a shift register. Right. Share screen again. Screen 2. All right, so now if we like Google 4021B, you will see that you will see that they already exist in my search history because I searched them up prior to making this lecture. But yeah, so here's the TI one specifically, but like in reality, you can have shift registers of the 4021B variety made by multiple different brands, and they will have slightly different model numbers, but if you Google them, they'll all have data sheets. We will click on this one. And as you can see, it's a CMOS 8-stage static shift register, which means nothing to me. But we will scroll down and figure out what exactly is going on here. We're going to ignore all that. I need to find the part where it talks about latch. Is that anywhere? Okay, well, regardless, I will find the clock speeds. Ah, here we go, clock frequency. So this is important. Basically, what we're looking for here is that we know that the shift register in question takes some sort of clock as input. And when we're configuring this particular like shift, when we're writing Verilog to interface with the shift register, we need to know what that clock frequency is. So in this case, it says that the maximum clock frequency for when you supply your NES controller with 5 volts power is going to be 3 megahertz. So the nice thing about the shift register in particular is that apparently you can use any clock frequency up to 3 megahertz to read from it, and it will still work, which is of course really nice because if you need to use it with a faster or slower clock speed to like sample at a faster or slower speed, you will have the option to do so. So that's like the main reason why you would look at the datasheet to find what this clock frequency is. And usually it'll be, at least the Texas Instruments datasheets are like really nicely formatted and stuff, so you can find this information easily. I remember Eugenia, you had to do like an assignment for M16 where you like had to look at a datasheet or something, which I thought was really funny. But honestly, it's kind of just a useful skill that I feel like a lot of people don't really learn because it's kind of, you don't have to do it unless you're in very specific situations. But yeah, so on this datasheet, we can find the clock speed, and then from there, we can go about actually like writing a module to interface with the shift register. But basically, you can read the datasheet yourself if you're curious, but what we gathered from this is that this shift register in question, you have to pulse a certain line that will indicate to the shift register to sort of like grab its inputs. And then after that, you basically pulse the clock over and over, and it will spit out the 8 bits that it has stored. This is how the NES controller works as a whole. So now if we go back to the slides. So yeah, our NES controllers follow a very simple scheme, right? When it's time to pull, we pulse the latch line. On each of the next 8 clock edges, we will read the input from the data line. And this will, one by one, it will give us the value of each of the buttons on the NES controller. And we can find the pulling clock, data clock speed, etc. from the data sheet. So sometimes the controller you use is more than just a few ICs inside, and like you unscrew it and you look at it and it's just like a mess that you don't know what's going on. So this was the case with the bongos, for example. And in situations like this, what you can do instead is you can actually figure out the protocol by connecting the controller to a device that it's meant to interface with. So like a device that already has a controller driver for it. And you can basically snoop on the connection between the two devices using a logic analyzer. We will quickly go into what a logic analyzer is, and then we will write a module for the NES controller. If any of you are not doing the DAV track and you don't feel like learning how to use an NES controller, which in this room appears to be none of you, Jonathan, are you doing the DAV track? Fair. Well, for the rest of you, if you you will be able to pay attention because you probably will end up using an NES controller or similar. But yeah, we will write that after this. Before that, we have means. This is the most important part of the lecture, by the way. Please make sure you pay attention. All right, moving on. So, logic analyzers. You probably have not seen one of these yet because they kind of hide in the DAV shelf or in Claire and my DAV kits. These are the logic analyzers, which basically you will use them to basically snoop on the connection between two devices. So I will run through the slides, which have like screenshots of everything, and then I'll actually show you the logic analyzer software. And just as an oscilloscope lets you snoop on an analog pin and see what the waves are, a logic analyzer lets you do the same thing, but for digital pins. And the nice thing about logic analyzers, especially ours, is that since they're software based, like you can, since it's just software on your computer, they also have a lot of fancy other features, like for example, decoding I squared C. So when you're working on your I squared C lab, if your nunchuck doesn't work, you can connect the logic analyzer to it and see what the waveforms look like and compare them to what they're actually supposed to be, which is really nice. So in order to download the software, we have a link here. These slides will be posted after, so you can find the software there. And when you open it for the first time, you'll probably see something like this, right? There's a bunch of empty lines, each indicating a logic analyzer channel. And then you can specify which logic analyzer you're using, which in our case is the LA 2016. And it will basically allow you to configure that logic analyzer as you wish. So the logic analyzer itself is going to look like this. It's like an octopus-like device, which I can actually go and get from my backpack. So this is what it looks like. It literally just looks like a thing with a bunch of tentacles sticking out of it. But yeah, each of these are like basically female connectors that you can put a jumper wire in. We also have like clips for these connectors that you can use if you are afraid of just sticking a cable into here. But yeah, we have these. So you will just connect these to your FPGA pins, like your GPIO headers, which are male connectors at the top, or you can connect them to jumper wires sticking out of your FPGA or of another connector. Like in our case, you might use these when you're with your nunchuck boards to connect to the JST to male jumper wires that you were probably given in your kit. And then, of course, don't forget to connect the ground on the logic analyzer to the ground on your board or your controller, because if you don't, it will probably just read garbage source. We did this many times when we were debugging and didn't know why our thing wasn't working. But yeah, so when you go back into the software, you can press that little gear icon and it will open an interface that looks like this. And you can actually look at the wires that you connected, like on here. Each channel is labeled with a wire that corresponds to that channel on the logic analyzer. And you can check those boxes to read those channels in the software. Then once you do that, you hit the play button, it will start sampling from the logic analyzer, and you can specify the sampling rate, the number of samples you want, etc., and it'll tell you how long it's going to sample for. And then you can actually like zoom in to see the details of your waveforms. And like I said earlier, if you're debugging I2C or some other standard protocol in particular, it has special decoding software that you can use to actually like look at what your SDA line is doing. So here you can see that it reads the SDA waveform and it's like, oh, this is a setup write and an ACK bit. Or, oh, this is writing a 0 and an ACK bit. Oh, look, we stopped the signal at the end. And of course, like you can see there's a random pulse here at the end that it kind of just ignores, because the logic analyzer can actually ignore noise like that. It only parses the actual, like what the final device will read. It's very cool. So I will actually open that as well. There are a few other things I want to note in the logic analyzer software that I think might be useful if you are making a DAV. Oh my God. There we go. So this is the software that I just described. I will note a couple of things. The first being that if you press the play button and it's yellow, it's not actually reading anything. I have yet to figure out what the play button does when you press it. Like it kind of just samples and then outputs random waves, but like it's definitely not anything that's actually connected to it, right? Like you can see here, I can zoom in and show you that there are in fact waveforms for SCL and SDA, but I don't know where these came from. They're not, it's not, my logic analyzer is not currently connected. The other cool thing is the logic analyzer software, I think is it here? Yeah, you can export data as like a text file or a CSV. And this is useful. Claire and I use this with our bongos when we were trying to figure out what the protocol was and how they worked with each other. So we exported the data as a CSV and wrote a Python script to analyze the waveforms and try to figure out which button presses corresponded with which like outputs. And so this might also be useful for you if you're using like a controller that you don't know the protocol for, such as, for example, I don't know, a duck hunt zapper or something similar. But yeah, that's pretty much it. This also has a PWM mode. I think you can analyze there with two particular channels on Logic Analyzer. You can analyze PWM signals. As of now, I don't think we've found a use for that, but I'm sure if you do find a use for it, please let us know. And then everything else here is fairly standard. You can like zoom in on a particular part of the wave and it will give you measurements like the width of the wave and the period, duty cycle, frequency, etc. It makes more sense to do that for SCL, for example, when you're trying to check if your clock speed is correct. it doesn't make sense to do it over SDA because that literally changes all the time. It's just, yeah, because this is an actual clock and this is not. And then if you look in analyzers, we have analyzers for I2C, for UART, SPI, CAN, and one wire. I don't know what those two are, but they exist. And apparently there's more analyzers as well that you can look at, but I don't think you'll use very many of them. And yeah, here are the decoded results. If you're trying to look at what your I2C module is doing with the nunchuck, you can like scroll through here and try to see what exactly is happening. Like for example, if you see a lot of stops or a lot of knacks, then you know that something is broken. All right, and with that being said, now I will screen share Cordis, which will, first I need to open project.
Why is it clock line in that?
Hmm?
Why is the clock line like not consistent?
Oh, so in the microphone?
Or in this whatever it's displaying there? That's like
Oh, why is it's because it that's okay, wait. That is a great question. I don't know why it's inconsistent between two of the actual reads. It might just be dependent on your I2C device. It might require that you like put space in between two of your reads or something. I'm not entirely sure. But as for like the rest of it, it's because when your actual I2C driver isn't running, your SCL line should not be doing anything. Or at least there's no reason for it to be doing anything because the whole point is to synchronize your two devices with on SDA. So if SDA is just like not doing anything, then your SCL doesn't have to either.
you know if it's just like supposed to be like driven high over here. Just left like
Yeah, so I think you can leave it floating. And in fact, when you leave something floating, the logic analyzer obviously cannot tell whether it's high or low. So it just picks one, I think, in to display here. That's also why you might see like random noise in okay. I don't see any here, but like sometimes you will just see random noise like fluctuations in your logic analyzer, and that can be because you left it floating. But yeah. So now for the NES controller, what we will do is I will. Right. You guys can see my screen. This is a skeleton for the NES controller. I posted it in DAV General if you want to go and find it there. And we will fill it in together. I'll give you guys a minute to go and find that. Did you all get a chance to get it? Cool. Oh, never mind. Yeah. You can ignore everything else other than this file. Just like create a Cordis project and put this one file into it, and then we will fill it in. So, first of all, in our actual, like, if you were to snoop on how the NES controller works, you would find that as we looked in the datasheet, the clock speed is up to 3 megahertz, and the polling clock speed is, I think it's 80 kilohertz. I don't remember if that information was found in the datasheet or somewhere else, but it was found. So, that being said, the first order of business, of course, would be to figure out when to pulse the latch line. Because if you remember, the latch line is how we actually grab data from our NES controller. So we will assume that NES clock, the input right here, we will assume that that is a 1 megahertz clock that has been divided for us. And NES data is the input NES like data line. And then we have to output the latch and the clock from our FPGA. Or rather, we have to output the latch from this particular module to tell the NES controller that we want it to start sending data. So in order to divide the NES clock, we can just use the clock divider that we made last time. So you can add the clock divider module from lab 2 into this project. And then the instantiation for the clock divider, you guys know how to do this. You answered a checkoff question on it. It would just look like this. Yeah, so as you can see, base speed, we have million, and then the output speed, 80 kilohertz. This is the reset line. I think I just gave up on resetting things for the time being. And then the output is polling clock, which is a wire that we need to create. We will just go like that. As you can see, the next order of business is to capture the edge of the polling clock. By the way, feel free to stop me if I'm going too fast at any point. But yeah, so the next order of business here is to capture the edge of the polling clock on which in an inside or always block that is triggered on NES clock. So this means, does anyone remember how we capture the edge of something in an always block? One of y'all definitely remembers. Yeah, shift register. So what we will do is we will create a shift register for the polling clock. And if you remember from like lab 2 or any other lab where you've had to do this, this is a very simple syntax that we've used every single time that basically assigns to this polling clock SR the like most recent bit in polling clock SR and then the new value of polling clock. And this will help us determine if polling clock has a pause edge by whether it was 0 before and is now 1. Anyway, we also need to create polling clock as like we have to actually declare it, so we will do that here. Everyone good with this so far? So far, the stuff that we're doing is fairly simple. The actual logic of reading the NES controller comes a little bit later. So if you'll notice, I gave you guys the code for actually like deciphering the controls on the NES controller, like basically the deciphering the output data. This is because I spent like a bunch of time working on it, and I came to the conclusion that the only way to reliably read the buttons was to just hard code each possible button press and the value of the data at that point. Which the annoying thing is our NES controllers don't support multi-touch for some reason, because this is a thing that happens where if you press this one button, 2 of the bits are high for some reason. My guess is it has something to do with the fact that they're third-party controllers and of lower quality. But yeah, as a result, this is how we will be deciphering the actual control outputs from the data that we read from our like NES controller. You look confused. I was pointing at you, Rachel. You good? Oh, okay, bet. Just wanted to make sure. Anyway. So now if it's time to pull the NES controller, meaning that if our polling clock has a pause edge, we need to pulse the latch line, which means we need to raise it, and then on a subsequent like clock cycle, we need to bring it back down. So what we will do now is also you're gonna notice that I'm doing everything in the sequential block, which is something that we told you guys not to do. But like realistically, the logic here is very simple and we were lazy. So we are doing everything in the sequential block. This will be fine because our clock speed is relatively slow. It's a 1 megahertz clock for NES clock. And also the logic is very, very simple. It's like 2 if statements. Anyway, so what we will do now is we will read the edge. Does anyone remember what value the shift register has to have in order for the polling clock to have a positive edge?
Is this active oil?
Hmm?
Is this active oil?
No, it's a clock. So
Oh. What clock is it?
0, 1.
it is 0, 1. Yeah, the reason it's 0, 1 and not 1, 0 is because we're not doing anything with our FPGA buttons, which are 1 when they're not pressed and 0 when they are pressed. This is just a standard clock. So this is 0 when the clock is low and 1 when it's high. Yeah. And at this point, we know that there's a pause edge, so we will raise the latch line. For the sake of formatting, I will do this. So now here's the other thing we're going to do. We are going to, otherwise we have to lower the latch line. So what we're going to do is now we'll go we can do that. And the reason we're doing it this way and not just like a really simple like sign statement is because this needs to be driven sequentially because it's going to be a clock that goes to our NES controller, so we want it to be stable. And theoretically, when you could do like the _D in our combinational block and like update it with that every single clock cycle. But also realistically, like I said, the logic is simple, so it's fine if we just have it all here. When you are informed enough to make those decisions when making your capstone, you are welcome to be lazy and put logic in your sequential block, as long as you know for a fact that it will work, and we will grill you on it if it doesn't work. But yeah, so the logic for driving the NES latch, of course, is very simple. However, there's one more thing that we have to do, is that we have to tell our controller module that we actually want to read data. So right now, our data, like we don't really know what is going to be on it, but we know that after we raise NES latch, for the next 8 cycles, there's going to be like, that we are actually going to be able to read things off of it. So what we will do is we will specify that if the NES latch is 1, we will enable reading. This is, now we're going to create reading as a reg, and we will initialize it to 0. And basically, for the 8 cycles after we start the NES controller, after we pulse the latch, we were going to let reading be high. That way we can use that as like a status indicator to when we are reading from the data line. Right. Is everyone good with what we've done so far? So far, what we've done is we've pulsed the latch line, and we have identified a point, at which we are allowed to start reading, and so we've created a status indicator, this reading flag, that will let us determine in our other parts of our logic where we can read data and where we can't. So does this make sense to everyone? Alrighty. And then lastly, if we're supposed to read from the controller, which means if our reading line is high, we will now actually, do so, and we will increment a counter that keeps track of how many times we've read so far. So we will increment a counter. Oh. And we will create that counter up here somewhere. Okay, this is gonna be 2 bits. 3 bits rather. Yeah, so this is being incremented every clock cycle after we start reading. And then next, now that we have actually we have a read counter, we can also use this as the index into our sort of controller, list our bits that we are storing internally to determine which controls have been read. So we will also create that. We'll go. Create that. And then we can just say, and if you think about it, right, like we have read count starting at 0 and incrementing by 1 every single time the NES clock cycles at this point. We have controls read that will, as a result, be assigned first to its 0th bit, then its first bit, then second, etc., all the way until we are out of bits. And each time it will get the value of NES data at that time, which is going to be a new value every time NES clock is pulsed. So this is why, if you pay attention to the timing of it all, you will see that this is something that works. And then lastly, if the read count is 7, meaning we have read 8 times already because we incremented to okay, if the read count is 7, it means that we have gone 0, 1, 2, 3, 4, 5, 6, 7. And then on the next clock cycle, that's when we will read a value of 7 in read count because of the nature of the delays that we incur when we're writing this or when this is running. So if read count is 7, that means we've already read 8 bits. So reading can be set to 0. And then from this point on, we won't read anything else. So now if you think about this, what we're essentially doing is we are, first of all, when the polling clock goes high and then low, we are pulsing the latch line. This in turn enables us to read. And as a result of that, we are incrementing a read counter and updating every single bit in controls read for 8 clock ticks. And then we are turning off the reading status indicator and we're waiting for the next pulse. Jerry, question?
Well, you have to reset read count, right?
You do, yes.
And then
Actually, you would, but we made read count 3 bits, so you don't have to because it'll overflow. Let me scroll up if I can find my cursor. Yeah, here we go. When you increment it from 7, it will go to 0 next, and then it will just stay there because reading is turned off by that point.
yeah.
But in theory, yes, if read count was not a power of 2, then you would have to reset it. Part the question.
Aren't you skipping the first bit for controls, right? Because you increment read count before using it.
Yes, but these are non-blocking. So theoretically, in hardware, these will happen at the same time. You will increment it, but the value that is, where does it? Oh my God, dude. Okay, you will increment it, but the value that's being read here is going to be still 0. So since it's non-blocking, this works. And also since it's a sequential circuit, we want to use non-blocking so that all the reads happen before all the writes in hardware. That's just kind of how it works. So as a result, we're not skipping the 0th bit. Any other questions?
Can you say again what the combination blocks down below does?
Sorry?
Can you repeat what the combination block is?
Oh, yeah. So this was experimentally determined that if you were to write all of this and just output controls read as your outputs, what it does is when you press a button on your NES controller, it will output the control bit for, it'll say the control bit is 1 for both that button and the one next to it. For example, I think the order of the buttons was something like, actually, I have no idea what the order of the buttons was, but if you run this, you'll be able to tell what they are. But yeah, basically, as a result of the fact that 2 bits were being set to 1 for every 1 button press, we had to actually figure out what 2 bits were being set to 1 for each button and decode it ourselves. This is just a layer that decodes the 2 bits into a 1-bit output.
We don't use the controls register anywhere else.
That's the output to our module. So you would then instantiate NES controller in your top level, and pass in clock in data and output latch and controls. And you would use the controls output from this module in your game or whatever else you want to use it in.
Okay.
Yeah. Any other questions? So that's just kind of how the NES controller in particular works, is that when you pulse the latch line, the shift register gets loaded with the values of each of the 8 buttons on the controller. So like when you raise and lower latch, the shift register grabs, I guess it latches onto the values of those buttons. And then for 8 cycles of NES clock, it will output them one at a time. So as a result, we need to raise latch ourselves to tell it to get those button values, and then we will read them out of the register. Any other questions? Cool. So once you do that, we will the next step is we will need to write a top level. The top level for this is going to be really simple. So you can like see it here. It's literally just, we will take a clock input. This is going to be our 50 megahertz clock, for example. We're going to take the data line and latch line, clock line, etc., wire them up, and we're going to output onto our LEDs, the controls for the output from our NES controller module. So that's all that this is doing. And as you can see here, I have assigned NES clock to the clock input directly. This is what I do when test benching. When we are actually running this, we will want to divide this into a 1 megahertz clock because the input will be 50 megahertz then. And we'll use a PLL for that. So I'll demonstrate how to create a PLL. Yeah, feel free to copy this module down. I can also just paste it in Discord. It is pasted in Discord. Now we'll go into IP components, and I will demonstrate how to create a PLL in the IP catalog. So normally what you would do is you would go into IP catalog, search for alt PLL, and you double click this LAD and it would create one. And you'd go through the steps of creating one. I will just go to the parameter editor because it'll show you the same exact things, and I don't want to create a new PLL for this. But at some point it will, here we go. So this is what it'll look like. Depending on your display settings, the GUI might look more scuffed because Quartus moment. But yeah, that being said, first thing you're going to want to do, you're going to want to set the in-clock frequency to 50 megahertz. That's going to be your base clock speed for the clock on your board. The other thing is select the PLL type automatically, and then all these other settings they should stay. Which output clock will be compensated for? I have no idea what these mean. We just stick with C0.
How long is this again?
Oh, you go into the IP catalog and search for alt PLL, short for Altera. Tools. Jesse, you had a question? Oh.
Wait, I haven't made that show opposite side, and right side,
Mm-hmm.
and like, there's like basic buttons.
Search for alt PLL in the top search bar in that menu.
ALT.
Yes, PLL.
Okay.
Ignore the reconfig one. I don't actually know what it does. I think that's like a dynamic PLL that you can pass in a clock speed to. I don't know how it works. I tried it once and it didn't work, so I gave up.
That's my turn.
All right. Jerry, let me know when you're caught up and I will continue.
Correct.
The main thing you'll want to make sure is set correctly on this menu is the frequency of the clock 0 input, which should be 50. Yeah, and also make sure your units are correct. It should be megahertz here. All right. Next, we will skip this tab basically. Or if you look at it, it might ask you to create a locked output or an asynchronous reset output or input. You can get rid of both of those. We can just have an input clock and an output clock. If you want to have a reset input, you can. I tend to not just because asynchronous resets are kind of weird.
What does a lockout mean?
I don't know. Not gonna lie. I haven't really experimented with the PLLs too much. All right. And then once you do that, it will tell you that it is able to implement the requested PLL. And then it'll ask you a bunch of other stuff. I think you can skip this tab. Oh, the page shrunk. You can skip this one, which asks you to create an input, a second clock input. You can skip this one, which allows you to dynamically reconfigure the PLL. And then here's where we actually configure our output clock frequency. So it's gonna give you a couple options. You can either select an output clock frequency in megahertz, nanoseconds, picoseconds, whatever you want. This is what I did. I just put in 1 here and then megahertz. Sometimes it'll tell you that it can't give you the exact frequency that you want, but it'll tell you that this is what it's going to do instead. And it'll usually be like a number that's kind of close to what you put in. Especially if you put in like a really small like frequency for your, or really slow frequency for your clock output, then it will tell you it's not able to implement it and it'll give you like a slightly larger number instead. So like something below, I don't know, 500 hertz might not work. Or honestly, something below like tens of kilohertz might not work. But you can experiment with that yourself. If you're going with something slower than that, you should just use the clock divider module that we made. Anyway, so you'll put in 1 megahertz. Alternatively, what you can do is you can specify a multiplication and division factor. But if you do this, it'll tell you what the multiplication and division factors are. For example, in this case, it's the multiplication of 1 and division of 50. Jesse?
It says it can't invoke their plus
Uh-oh.
stage or
This one?
yeah.
Did you make sure that this is 50? This is select PLL type automatically, and this is normal mode? Okay. And then everything else should be like as is, except if you want to get rid of an asynchronous reset and locked output, you can. But yeah, that should hopefully fix it. And then here, once again, 1 megahertz. These are multiplication division factors. You don't really need to worry about them. You can also specify a phase shift if you want. I don't think we ever have. Same with duty cycle. It defaults to 50%, I think, and you can leave it at that. And then if you want to create more PLL outputs, you can. So you can select use this clock and you can actually create multiple PLLs. I think our FPGAs have 5 in total that you can create. So if you want to create more than 1 PLL clock, you can. We will not be for this. We only need the 1 megahertz one. So we'll skip all of these. Then we'll just click next, check all the boxes except for the ones that say VHDL or AHDL, and then finish. I will not overwrite everything because I don't know if my PLL is the same as before. It should have been, but yeah. And then once you do that, just like with the ADC, it should show up in the IP components list. Yeah. Anyway, so once you've created the top level, you've instantiated a PLL. Cool. This is literally all you need to make the NES controllers work and display things on your LEDs. So now if you were to try and actually like wire this up to your FPGA, it would be really simple. You just take your NES controller, you grab one of these things, which are basically like these will connect one end to your NES controller, and the other end will connect to pins on your FPGA. We'll post the pin out for that like after this. I forgot to add it to the slides, but I think it was like actually I'm not going to try and recall what it was, but yeah, just grab one of these and your NES controller output, like your cable port thingy, will go in here. These will go into your FPGA. You can use the Arduino IO pins since they're all female connectors. And yeah, that's pretty much it. You will be able to it'll just work ideally. Yeah. And that's pretty much it for this workshop. If I go back, I will verify that, yeah, there's literally nothing else. So thank you guys for listening. Those of you who are working with NES controllers, feel free to grab one of these from up in front. Anyone working with a microphone, if you need a microphone, message me or Claire. If you need an NES controller, message me or Claire. And that's it, guys. Thank you for listening. I can find my